In the previous video, we discussed the Pythagorean scale. A problem that arises with the Pythagorean scale is with transposition. When we made our scale based off of the note C as the fundamental, we got the following scale and related interval ratios. If we wanted a new scale where F was the fundamental, we can transpose this whole scale up by a major fourth and then shift down an octave when we need to. For example, we can take the note G and transpose it up a fourth by multiplying by 4/3, and we get 3/2 times 4/3 equals 2. This means we transpose the note G up to C. To see another example, let's see what happens to A. We take 27 over 16, multiply by 4/3, and that equals 9/4. This is greater than 2, so we shift down an octave by dividing by 2. This gives us 9/4 divided by 2, which is equal to 9/4 times 1/2, which is 9/8. This means the note A transposes to the note D. In fact, all but one of the notes transpose very easily. C transposes to F, D transposes to G, E transposes to A, and B transposes to E. The only difficult note to transpose is F. Let's see why by multiplying the fraction for F by 4/3. We have 4/3 times 4/3 equals 16 over 9, which is less than 2, but it also doesn't show up on our list. It's with this new note we discover a problem. The new note is called A sharp, and it is between A and B, since 16 over 9 is between 27 over 16 and 243 over 128. Furthermore, this new note is not exactly between the two, meaning the fraction that we would multiply 27 over 16 by to get 16 over 9 is not the same as the fraction we would use to multiply 16 over 9 to get to 243 over 128. In fact, 27 over 16 times 256 over 243 equals 16 over 9, but 16 over 9 times 2,187 divided by 2,048 equals 243 over 128. The fractions in red represent new intervals. This problem of creating new notes and new intervals extends infinitely, and this is why transposing in the Pythagorean scale falls apart. Around the 16th century, some of the intervals in the Pythagorean scale were changed to simpler fractions, and the just intonation scale was created. But transposition was still a problem. The solution for transposition was not a historically new idea, but it became the popular scale in Western music and is still the one heard today in most popular music. The solution was to divide the octave into 12 equally spaced intervals using the 12th root of 2, which is the same thing as 2 to the 1/12th power. And the name for the scale is equal temperament. We can compare the Pythagorean and equal temperament scale with this chart, with the intervals listed in decimal form. To hear how the two scales relate, I'm going to play the same Pythagorean scale I did in the last video, and then play the scale again, but using equal temperament tuning. Remember that we based our notes off of a fundamental frequency of 92 Hz. First, the Pythagorean scale on its own, showing the tuning for each note. Next, the audio we'll hear is the equal temperament scale, which sounds almost the same, but at the top of the screen, I'm displaying the tuning for each note from the Pythagorean scale, while at the bottom, we see the tuning for the equal temperament scale. Notice how the numbers differ. To the classically trained ear, equal temperament can be difficult to listen to, but it is with this scale that we can transpose. Let's see that with the same example I used before, transposing F up a fourth. To do this, we have to notice that a fourth in this scale is the interval 2 to the 5/12 power to 1. What we get after transposing is 2 to the 5/12 times 2 to the 5/12 equals 2 to the 10/12. This is a new note, again called A sharp, and it is between A and B. But more importantly, the interval from A to A sharp is the same as the interval from A sharp to B, 2 to the 1/12 to 1. This is because 2 to the 9/12 times 2 to the 1/12 equals 2 to the 10/12, and 2 to the 10/12 times 2 to the 1/12 is 2 to the 11/12. What this demonstrates is that the equal temperament scale preserves the intervals between the notes after transposition. There are many discussions that can be had about which particular pieces of music sound best in certain tuning scales, but it is a fact that equal temperament has become the popular tuning method for modern Western music. It is interesting to note that what has become standard is a tuning method that involves the irrational number 12th root of 2, which is quite a progression away from the rational numbers we started with in the Pythagorean scale.